Good morning, everybody. My name's Will Bailey. I'm an Android engineer at Instagram. And today I'm going to talk about creative tools engineering at Instagram, and specifically how we built two recent tools for Instagram stories, and how we designed and engineered them on Android. But before we get started, I'd like to dive in a little bit and talk about why do we build creative tools? Why is it important? For me, I'm inspired by the creativity I see from the Instagram community. Millions of people around the world are creating every day on Instagram. I believe this type of creative expression can help people strengthen relationships and enjoy their lives more by seeing and sharing their world in new ways. Enabling that kind of creativity through design and engineering is what I love about my job. Whenever we ship a new creative tool, it's so exciting to see how it will be used, and we're always surprised by what people do. So what makes a good creative tool? I think these four principles frame it nicely. An ideal creative tool should be flexible and usable and discoverable and delightful. By flexible, I mean that we don't want to be overly prescriptive about how a tool is to be used. It should inspire the user to see the world in a new way, and it's the best when people come up with their own way of using the tools that we provide. That flexibility should be balanced with usability. Although the technology behind the scenes is powerful, we want the user to be able to achieve these effects in an effortless way. Discoverability means we want these tools to be easy to reach and top of mind whenever the user has an intent to share on Instagram. Finally, we want to bring delight and fun to the platform with tools that help people connect with their friends in entertaining new ways. So to start with, I'd like to talk about sticker pinning, a creative tool we released this summer. Back in December, we introduced stickers to Instagram stories to help our community add context and creativity to the photos and videos they share. With stickers, you can tag the coffee shop you're at with the location sticker, tell your friends that it's getting chilly in SF with the weather sticker, or celebrate Halloween with spooktacular illustrations. We soon realized that stickers worked well for photos, but felt static and less native on videos. Video is a huge part of Instagram stories, so we wanted to see if we could do better. So we set out to build a feature. Oops. So, sorry about that. So we set out to build a feature that let you pin stickers to any of your videos, and we call that sticker pinning. And here's an example from Mother's Day. It's so fun to see the stickers pinned as you pan across the scene. And it also works with Zoom, as you can see here. Our designers went through a number of prototypes to ensure that sticker pinning feature aligned with our principles of building flexible, usable, discoverable, and delightful tools. Let's take a look at a few of the early ideas. We felt it was important to give users the right amount of control. We explored and prototyped many versions of the editing mode ideas so that it was easy to select the right frame of the video. We saw in research that being able to scrub back and forth was a small but impactful UI change that made it a much nicer experience to select the subject to track in the video. We also wanted to give control over what the sticker was pinned to. Here's an early exploration of the anchor point idea, where you could set an anchor that the sticker would follow. We dug deep into this direction and ultimately landed on having the anchor center on the sticker itself. It covered most of the use cases and kept the experience light and simple. Lastly, we had to find the appropriate way to introduce this feature. We explored everything from having a button to enter pinning mode to automatically pinning all the videos. All had trade-offs. We wanted this feature to be discoverable so people could use it, but not mandatory for those who didn't want to. So it seemed that teaching the users about the new feature and having it under a gesture was the right balance of being discoverable but not too disruptive. So with the design ready, we set about implementing this on Android. And to break down the process of building this, I'll talk about these 4 components of the build. First, general sticker layout and manipulation during the edit step. Next, the video frame selection UI that allows the user to scrub through the video to find the subject that they want to pen to. Then I'll talk about some details about how we integrated with a native region tracking library developed by the Facebook Applied Machine Learning team. Finally, how we render the region track stickers into the final output video. For laying out and manipulating stickers, we use a special view called the interactive drawable container. This view provides touch handling to perform pan, rotate, and scale gestures on any number of interactive drawables. Interactive drawable is a thin wrapper around a standard Android drawable that keeps track of its transform state. This allows us to use any drawable as a sticker wrapped in interactive drawables. We can create any number of custom drawable classes to render different types of stickers, some of which use data like the weather, location, and hashtags, and some of which are just illustrations. The framework is flexible and allows us to add more types easily. Once we have a sticker on the screen, we need to help the user select their subject to pen to. The design called for a scrubber that allows the user to seek through the video. Smoothly seeking through a video requires a bit of lifting, but in this case, we're able to leverage some of the existing code from the Instagram feed creation flow. The basic approach here is to have a seek bar widget that the user can pan their finger along to target a particular frame in the video. This target frame time is passed into a scrubber render controller. The scrubber render controller wraps a media codec and media extractor pair. Media extractor allows you to select tracks from a media source and extract encoded data. The encoded data is then passed to a media codec instance to decode the data and render it onto a surface. This is displayed in a texture view, allowing the user to visually seek through the video. And that's what you can see here. If you noticed in the video, scrubbing forward is a bit smoother than scrubbing backward. This is due to a concept in video encoding called group of pictures, or GOP. A group of pictures represents a sample of frames from an encoded video and can contain a mixture of iframes, p-frames, and b-frames. Intra-coded pictures, or iframes, contain the full image. An iframe signals the beginning of a group of pictures and offers a clean random access point such that decoding can start cleanly on an iframe, and any errors within the GOP structure are corrected after processing a correct iframe. Predictive coded pictures, p-frames, and bipredictive coded pictures, b-frames, both allow for better compression of the video media. P-frames can use data from previous frames to decompress, and b-frames can use both previous and forward frames for data reference for even higher compression. The cost of this better compression is that you need to decode starting with an iframe in order to decode P and B frames from a video. When you're scrubbing or playing forward, this is natural. However, when going backward, this means you need to seek to the prior iframe and then decode forward until you reach the desired intermediate frame. This makes going backward a bit more expensive. The interval between iframes can be configured, but a higher frequency of iframes means less compression and larger files. Buffering a number of decoded pictures outside the current position can make this smoother, but also incurs additional memory overhead. I also mentioned some of the media APIs on Android, like Media Codec and Media Extractor. You could give a whole talk on working with these APIs. They're low level and can be challenging to use properly. The core idea is receiving empty input buffers from the media codec, filling these buffers with encoded data from a media extractor, and placing them back and passing them back to the media codec. The media codec can then decode the data to a surface or to an output buffer. Media Muxer allows you to multiplex multiple AV streams into an output file. The Android documentation on these low-level media APIs has gotten better, but I also recommend checking out the media codec docs on bigflake.com, where you can see examples of doing various types of tasks with these APIs. So once the user selects the desired video frame, The next step is to feed the video frame data to a cross-platform native region tracking library. We wrote a video frame reader class that uses media codec and media extractor to decode the video and pass the frame data to the region tracking library. From the region tracker, we receive back the transformed coordinates for the tracked region in each frame of the video. We store this data and use it to animate the sticker in the edit step and ultimately burn it into the final video before uploading to the server. Here's what that looks like in a diagram. When the user requests to pin a sticker by tapping Pin in the Frame Selection Scrubber UI, we request the region tracker controller to start region tracking. Frame reading is provided via a delegate. This delegate manages frame readers that read the video forward and potentially in reverse. It also coordinates with the user interface to display progress as the frames are read and region tracking proceeds. As frames are decoded, we read them into byte buffers by calling glReadPixels to pull the data from the GL surface and that the video frame reader's media codec is decoding to. Reading pixels off the surface with glReadPixels ensures that we have a consistent RGBA color format for passing the frame data to the region tracking library. The region tracking controller receives these RGBA pixel buffers in on-frame read and passes them on to the native region tracking library with quaternions from the gyro tracker if available. The region tracker runs an algorithm on the frame data and spits out the coordinates for the targeted region in the particular frame. The region tracking controller caches the data in an ordered set that we can use to display the sticker at the appropriate coordinate for this time sample of the video. Since we support pinning in the middle of the video, we may need to pass frames to the region tracker in reverse order to know where a given region was at the beginning of the video. If the pinning target is not the beginning of the video, the region tracking controller delegate first transcodes the video into all iframes to provide fast backtracking. It then provides two video frame readers to the region tracking controller, one that seeks from the start position backward to the beginning, and one that seeks from the start position to the end. Our friends on the iOS team had an easier time with this. The built-in media player in AV Foundation on iOS supports a frame rate of -1 and handles reverse playback automatically. We had to build this functionality ourselves, but as you'll see, we got some halo benefits from this work. One of the coolest tricks you can do with region tracking is to track an object that is out of frame at the beginning of the video. The tracker takes gyroscope samples as normalized quaternions with each video frame we pass to the region tracker if available. The gyroscope data helps the tracker keep track of the frames that have exited the viewport by approximating where they would be based on the phone's change in orientation. If the video is imported or the device does not have a gyroscope, the tracker falls back to just using the pixel data. The real magic behind this feature is provided by a C++ library that we use on both iOS and Android. This tracker is built and maintained by a core team at Facebook called Applied Machine Learning. This team channels R&D into applied solutions that power creative tools across all the Facebook app family. Here's a bit about how the algorithm in the region tracker works. Given a video frame, we extract a much smaller area, which we call the region of interest. And with this region of interest, we use a computer vision technique called correlation filtering to compute the final tracked region. Correlation filters build a dynamic model of the object on the fly as it is being tracked. Here we show, for the given input video frame, the extracted region as well as the evolution of the corresponding model which produces the desired tracked output. This technique is robust to a variety of non-ideal factors that may affect the video, such as camera shake, scale change, partial occlusion, and even lighting variation. The tracker is initialized with a region for the first frame, either a center point or a rectangle. The tracker takes each frame it's given, converts the frame to grayscale for simplicity and efficiency, and then outputs the coordinates of the target region in that frame. After region tracking is complete and the user is done editing, we need to perform a final render before uploading the media to the server. In this render, we burn the sticker into the video at the appropriate coordinates based on the tracking data. First, we make a bitmap of the sticker drawable. Then we upload that bitmap to the GPU as a texture. We transform the texture to the appropriate coordinates for each frame based on bounds data from the region tracker and blend it with the video frame for encoding into the final output video. So there are a lot of moving parts in this feature to organize, and beyond the base complexity, there were also platform challenges. We initially tried to implement real-time tracking during video playback. However, we found that the frame rate we could achieve was not sufficiently smooth on some lower-end Android devices. The biggest bottleneck we ran into was the time to copy image data from the GPU to the CPU via GL read pixels. We tried to mitigate this by downscaling the video we used for tracking. However, this negatively impacted tracking accuracy. We settled on the solution of background tracking with a progress spinner, as we felt this was a good user experience and addressed the frame rate problem. Another challenge was the support level for media codec. Instagram supports API level 16+. However, media codec is not well supported below API level 18. We chose to gate this feature to API level 18+, which accommodates about 95% of our user base, rather than spending a lot of time trying to solve the media codec issues for the minority of users on older OS versions. So that was region tracking and sticker penning. Now I'd like to talk about kind of a side benefit that we got from building that feature, and it's the rewind format, which is our term for reverse video in Instagram. We've seen some really fun uses of this feature by the community since it launched. Playing a video in reverse can make it seem like you have superpowers, like levitating something off the ground into your hand or performing an impossibly high jump. And one of the great things about working at Instagram is that everyone can be a part of the product development process. In the case of Rewind, the engineering team proposed the feature after we built the technology to support video backtracking for sticker penning. It was easy to spin up a demo to show how fun making reverse videos could be, and our project manager and designers helped us shape the demo into something that we could ship. One of the interesting design decisions we made was whether the feature would be better as a pre-capture or a post-capture feature. The initial demo was to do this post-capture. This allowed you to reverse any video and gave you a lot of flexibility, but it didn't really advertise the feature, and we felt like offering this as a pre-capture format helps the user understand what they could do with it and made them think about capturing in reverse as a creative form of expression. Crumpling or tearing paper, pouring liquids, or dropping things all lead to magical results when played in reverse. We think that offering this as a pre-capture format has helped inspire the creative uses we've seen. Encoding a video in reverse means that we need to start with the last frame and encode frames backward to the beginning. If we have to wait until the video is fully recorded to start encoding, then the processing delay will be substantial. We can improve this by buffering short clips of the video and reversing these clips while the forward encoding is still happening. However, the buffer needs to be managed as this incurs additional memory overhead. The solution was to overlap reverse encoding with forward encoding. And here's how that works. As we record, we receive GL frame buffer textures and place them onto a stack. When the stack reaches a configurable limit, we start flushing the frames last in, first out to a media codec to encode a short reversed clip. In order to keep from blocking the recording thread, we pass frames to the reverse encoder at the same rate that we receive them from the new frames from the camera. The new frames are placed onto a second stack, which we swap to the encoder as the first stack is depleted. At the end, we just need to flush the last short clip before we have all of the reversed samples. We then use a bridge to FFmpeg to run ffconcat on the short reversed clips, stitching them together in reversed order to form the complete reversed video. ffconcat runs very fast, so the only latency we really add here is the time to process that last clip. And here's how these components work together. Our camera infrastructure sends us frames to a reverse frames handler. The reverse frames handler stores inbound frame buffer textures on a stack and encodes the stack via a media codec instance into a temporary clip file. The internal state of the reverse frames handler is managed by a simple state machine as it moves between idle, encoding, and finalizing states. Once the final clip is encoded, the reverse frames handler signals the reverse capture controller, and the reverse capture controller then feeds the clips to ffconcat, generating the final output. Reversing audio is a bit simpler than video. The data is small enough that we can keep an entire 15-second audio clip from the microphone in memory. We receive the audio samples from the microphone as PCM16 byte arrays. To reverse these, we first convert the byte buffer to a short buffer to pair the 16-bit samples, and then reverse the short array. This encoded data is then muxed with the video data using Media Muxer to produce the complete reversed AV media. We mute the sound by default in the edit step, since most of the time audio is distracting to a reversed video, but there are some cases where you can make hilarious effects by reversing yourself talking backward, which leads to a very awkward sounding forward recording. So I hope this talk has given you an idea of our approach toward building creative tools at Instagram and some of the types of engineering challenges we work on. A couple of takeaways. Low-level media hacking on Android is challenging, but with persistence, you can achieve amazing effects. We're constantly building new experiences like this at Instagram, and it's so much fun to see how the community uses what we've made. If you enjoy this kind of creative coding, please come join us. And thanks very much. If there's any questions, I'll try to answer them. Thank you.